In this recording, we're going to look at the beginning of our immune system. We call it our innate immunity. There are several lines of defense when it comes to our immune system. The innate immunity is really our first line of defense, as well as our second line of defense. Now, the word immunity, or the word innate, means born with. So innate immunity, this is something that our body has always had. It has never had to learn it before. It's never seen things before. It's just things that are already in our body, ready to go as part of our immune system. And so I'm like, that's the basics, and I'm like, of this entire chapter is what are those first and second lines of defense, because there are 3 lines of defense in our immune system. The innate immunity is both our first and second. And our first line of defense, this is kind of where we're going, I'm like, is our skin, our mucosal membrane. And then our second line of defense really gets into a lot of cells and processes. This is probably a better slide. So our innate immunity, external skin barriers, pretty much just preventing things from getting in the body. Second line of defense is really, all right, things got into the body that shouldn't be there. What are things that our immune system has to fight those things off once they've gotten in? Whether it's certain cells, chemicals, or other processes, their job is just to find anything that doesn't look normal and get rid of. I'm like, so innate immunity, first 2 lines of defense, this chapter. The next chapter, chapter 16, is all about adaptive. This is recognizing things they've seen before, forming memories, and it's a whole nother white blood cell that takes care of it, the lymphocytes. So I'm like, we'll get into that, and I'm like, no, and I'm like, in the next chapter. But right now we're just going to focus on these built-in responses that our immune system has. Again, another little slide that just talks about the innate or non-specific immune system, meaning it's just looking for anything foreign, tries to get rid of it from the body. So starting with our first line of defense, our best first line of defense we have, again, is trying to just prevent things from getting into the body at all, and our skin does an amazing job of that. Now, some ways that our skin helps prevent things from getting in. One, and if we start remembering some more general A&P and advanced A&P review, the skin has 2 major layers. It has the epidermis and it has the dermis layer. Well, that top layer has lots of, multiple layers of tightly packed cells. Now, by having these multiple layers of tightly packed cells, and I'm like, it helps in a couple different ways. One, and I'm like, because it's so many layers, and I'm like, things can't always penetrate through all of those layers of cells. So it's this great wall. Also, these cells are shedding all the time. And if a microbe lands on your skin and is trying to get in, well, as your skin cells are shedding, some of those pathogens shed with the skin cells. And so I'm like, it's a great way. Also, in the epidermis, we do find, near the bottom of the epidermis, but we do find dendritic cells. Dendritic cells can phagocytize, aka eat, and I'm like, pathogens that are trying to penetrate past that epidermis layer. The dermis layer underneath, and I'm like, is a lot bigger than the actual epidermis itself, and I'm like, it's kind of claimed to fame for the immune system is that it has collagen fibers that help resist abrasion. And I'm like, meaning it helps resist, it keeps our skin a little softer, flexible, so that it doesn't crack, it doesn't break. And then anytime you have a crack or a break in your skin, you now have an open area for pathogens to get in. It does also, and I'm like, have some blood supply as well, which can bring in certain white blood cells to fight infections as well. Now, other parts of our skin, other than just having those outer layers, and I'm like, other things that our skin also has that can help us fight against pathogens are various chemicals. One is your sweat, your perspiration. How your sweat helps. Your sweat has 3 things in it to try to prevent microbes from getting in or colonizing. One, your sweat has a lot of salt in it. Salt itself inhibits the growth of most pathogens. You're right, there are some pathogens that can grow in the presence of salt, but most don't like that high salt environment that our sweat provides. Also in your sweat, you have antimicrobial peptides. These are proteins that inhibit the growth of pathogens. And then we also have an enzyme found in there called a lysozyme. Its job is to break things down, and it can actually start to destroy or break down bacteria cell walls. Also, another chemical that our skin can make, or at least another secretion, is sebum. And I'm like, that oil. Now, two ways that that oil can help for our immune system. One, that oil keeps your skin soft and pliable, also making it less likely to break or tear, providing an entry source for pathogens. And that oil actually lowers the skin's pH slightly, which for some is enough to inhibit the growth of certain microbes. It's out of their optimal pH range. And I'm like, our skin is doing awesome things from, just to try to prevent microbes from getting in. Now, also in that first line of defense, preventing things from getting in, are our mucous membranes that line all those body cavities open to the environment. Now, I'm like, it also has two distinct layers. It has that epithelium layer, just like your skin does, and then it has a deeper connective tissue. We're not going into all the names. Now, how that epithelium helps is really in 4 ways. You wouldn't think this one little layer here has 4 different ways it can help prevent microbes from getting in, but it does. 1, we do find some dendritic cells in that epithelial layer. And again, just like the dendritic cells in your epithelial layer of your skin, they do go around and try to phagocytize or eat pathogens. Also, we find goblet cells and we find ciliated cells. And I'm like, goblet cells make mucus, and the cilia's job is to move the mucus. Well, by having that mucus there, it helps trap invaders in the sticky mucus, and then the ciliated cells help sweep it out of there to try to get it out of our body. Also, there's a secretion that epithelium can make is an antimicrobial peptide, similar thing found in our sweat. Again, it's a protein that inhibits microbes' growth. And the epithelium, like our skin, also is constantly shedding. And I'm like, we're constantly making new cells. And as it sheds, yes, some of the pathogens also fall off with it. The deeper connective tissue below it doesn't have too much claim to fame, except it's there to support that epithelium layer, because that epithelium does so many great things. Now, also another part of our first line of defense is that normal flora bacteria, because we do have a lot of bacteria that are living on our skin. We do have bacteria that are living on the mucous membranes, and by having those bacteria there, your normal flora bacteria, it provides what we call microbial antagonism. It pretty much just means that your normal flora is going to compete with potential pathogens. And I'm like, they've already found themselves a home. They do not want invaders to come in. And I'm like, partly is because they're using up the nutrients that are there, making less available to pathogens. And as your normal flora produced waste products, it also makes it not a great place for pathogens to want to call home. They also can provide an unfavorable condition or environment. Some of these normal flora can change the pH. Some of the normal flora can actually make antimicrobial compounds. Yes, and I'm like, a microbe can make antimicrobial compounds. They just work against other things, not themselves. Some of your bacteria can stimulate their second line of defense, which we're going to get to. And then some promote the health of the body, which really just is promoting the health of the immune system in the body, because some make vitamins that for the host so that the host is healthy as well. So our normal flora really can help us out and actually are part of our immune system. Now, second line of defense, it's pretty much microbes or pathogens have gotten in. Even though the skin and the mucous membrane prevent a lot of things from getting in, however, yes, sometimes things do get in. And so we have to have our next line of defense. Once I got past the first, now what do we do? Things we find in our second line of defense, there are cells, there's chemicals, and there's a whole bunch of processes. And a lot of these all are found or originate in the blood. And I'm like, so we're going to kind of look at what's going on in the blood. Now, things we find in the blood, we have unformed elements, aka non-cells, and formed elements, aka cells. And I'm like, the two unformed elements that we find in our blood, plasma is the biggest one. Plasma is mostly water. If you've ever donated plasma, water is not what they're paying you for. They're also not paying you for electrolytes. That's just talking pretty much salt. But things we find in plasma, nutrients, proteins, clotting factors, antibodies, and iron binding compounds. What they're paying you for are some of the proteins, some of the clotting factors, some of the antibodies. That's what you get, the big bucks, but they get way more for your plasma. Now, another term that's very similar to plasma is serum. And like, serum is very much like plasma. It's all the fluid except the clotting factors are removed. A lot of times if they're trying to replace fluids in patients, they would give them blood serum. And like, they would not want to give them plasma because those clotting factors, and I'm like, would cause unnecessary clots. And I'm like, and a lot of times if a patient has lost a lot of fluid, they probably have an open wound somewhere that's already going to trigger clotting. So we don't want to trigger more clotting. Now, some of these formed elements, aka cells, that we find in our blood. One, we find erythrocytes. Erythrocytes are your red blood cells. Their main job is just to carry oxygen and carry carbon dioxide to a lesser extent in your blood. We also find platelets. Platelets are there for blood clotting, but they can also help with inflammation. And we'll talk in a little bit, inflammation is not a bad thing. Then we have leukocytes. Leukocytes, if you break it down, anything cyte means cell. Leuko means white. These are your white blood cells. I'm like, these are the main ones that are involved in defending the body against any invaders. So these are the ones we're going to focus on, are these white blood cells. Now there are 5 different white blood cells, and we group them into granulocytes and agranulocytes. And I'm like, we'll take a look at our granulocytes first. But this is just showing some of these cells, and I'm like, these formed elements we find in our blood supply. That the different cells, yes, and I'm like, the red blood cells are there, but they're just really there for transporting oxygen. And I'm like, however, we have platelets, we have basophils, we have the neutrophils, we have the eosinophils, we have monocytes, and we do have lymphocytes. They're part of our immune system, but they're our chapter 16 part of our immune system. It's these guys that are part of that second line of defense. And so we're going to start looking at, or first talk about those granulocytes. Now they're called granulocytes because they have really large granules, hence their name, that usually pick up the stain found in their cytoplasm. So you can see these staining granules in their cytoplasm. Now there are 3 types of granulocytes, and they all end in "phil." There's basophils, eosinophils, and neutrophils. Now, the basophil's job is really to help in part of the inflammatory response, causing inflammation. Again, inflammation is not a bad thing. Eosinophils and the neutrophils, these guys are really helping to phagocytize pathogens. And I'm like, to go ahead, try to find them, eat up, somehow destroy these pathogens. And the cool thing about neutrophils and eosinophils is that they can do what's known as diapedesis. And again, I like to break apart words. Dia means through, like going through. Hence, if you think of the word diarrhea, it goes right through you. Anything ped has to do with your foot. And people are like, I still don't get it. And I'm like, the word itself translates into walking, hence feet. And I'm like, through. Now, what these cells can do is they can walk through walls. Now, they don't physically walk, and I'm like, they don't actually have any feet, but they can travel through walls, through capillaries, so that they can squeeze places and go towards infections. And so I'm like, we could find some of these sites. This is looking at one of those white blood cells, and I'm at the neutrophil, and it realizes that there is some type of invader here, some type of bacteria got in. It can squeeze through blood vessel and capillary walls. It's really small. And I'm like, but they can squeeze through, so they can go right to where that infection is and start phagocytizing and getting rid of those invading pathogens. Now, the other group of our white blood cells, we have 2 more left, and I'm like, out of the 5, are the agranulocytes. Just means they don't have granules in their cytoplasm. So their cytoplasm looks kind of boring. And there are 2 of them, and they both end in cyte. So the ones that have granules, their names end in "phil. The ones that don't, they all end in cyte. And there are 2 types. There's lymphocytes and there's monocytes. Lymphocytes are involved in adaptive immunity, chapter 16, so we're not going to talk about them too much in this PowerPoint. We're going to wait. And then monocytes. Monocytes can also leave the blood, and they mature into what we call as macrophages. Now, the word again means, macro means big, phage means to eat. They literally turn into huge eating cells. They are a lot larger than other white blood cells. They are big, huge eating cells. Now, a helpful mnemonic to remember the quantity of the different types of cells, because some of these white blood cells are more common than others in your blood, is the never let monkeys eat bananas. It just means that neutrophils out of the 5 white blood cells are the most abundant, followed by lymphocytes, monocytes, eosinophils, and finally basophils are the rarest of the white blood cells. Now, why we care about quantity of white blood cells? And I'm like, because if there's a change in those white blood cell counts, it can kind of clue you in on what's going on. Again, a lot of times if they don't know what's going on with a patient, they're going to draw blood and analyze it. And a lot of what they're doing is counting various types of white blood cells. And I'm like, because if you have an increase in eosinophils, it's kind of a big clue that you probably have some type of allergic reaction to something going on, or a parasitic worm infection. They're like 2 completely different things going on, but yet both will cause an increase in eosinophils. Increase in neutrophils is an indication there's a bacterial infection somewhere, and an increase in lymphocytes is an indication you have a viral infection somewhere. So it can help you narrow down what's going on when they're looking at your different blood cell counts. Now, other than cells, the next really big part of our second line of defense are various processes to get rid of pathogens, such as phagocytosis. There's also non-phagocytic killing, so killing without eating. Then there's chemicals that can defend against pathogens, inflammation, which again is not always bad, and fever. So we're going to start with the phagocytosis. Now, it's a multi-step process, and I'm like, the first thing is, I'm like, well, first, here's one big, huge phagocyte. It's a big eating cell. There's the nucleus, it's a cell. And I'm like, and here's the microbe. And I'm like, they, a real actual picture, and then they kind of cartoonized it. And yes, and I'm like, so this phagocyte is going to see these microbes. And I'm like, there's usually some type of chemical that microbes are giving off that attract phagocytes to it. And so it's going to find these phagocytes. 2, and I'm like, is adherence. And I'm like, this particular phagocyte is going to try to adhere or stick to some of these microbes. Then you have ingestion of the microbe into the phagocyte. It literally is eating it. It is now getting inside of that phagocyte. We call it the hug of death. You can even see this even looks like it's trying to go around and hug this microbe, aka hug it, bring it in, eat it. Then you have a lysosome, whose job is to break things down. Lysosome fuses with this little vesicle that has your bacteria in it. And I'm like, and all the enzymes from that lysosome are going to break apart and kill the microbe. And then we have the elimination or exocytosis. Let's get rid of any of that bacteria, any of the enzymes out of the cell. And that phagocyte is just going to keep eating. Lysosomes are going to keep breaking them down. They're going to keep spitting them out. But it's this kind of 6-step process on how the actual cell does phagocytosis. And I'm like, it's a nice, good process to know, wink, wink, hint, hint. And I'm like, here's just another picture. They just break it down into 5 steps. Same basic idea. Phagocyte attaches. And I'm like, they just eliminate that's going towards it. And I'm like, it attaches it, it brings it in, and so now you've got that bacteria in a big old vesicle. Lysosome is going to fuse with it, digestive enzymes break it down, then you have exocytosis, getting rid of that broken down bacteria. And like, this is a picture of a cool phagocyte, and I'm like, macrophage, big eating cell, that is using little cytoplasmic extensions. It's almost kind of like Spider-Man sending out these little webs. And I'm like, to trap and stick to bacteria, all the green things, and literally pull it in like a little tractor beam. And then it's going to ingest them and get rid of them. Now, another process that we can get rid of microbes, and I'm like, it's called non-phagocytic killing. So it's not eating, and it's really the job of some of your eosinophils. Now, eosinophils are a big white blood cell that's there to attack parasitic helminth infections, aka if you have a worm infection. Now, how it does it is it generally secretes toxins. It will coat the worm, secreting toxins that are going to weaken or kill the helminth. So here is a parasitic worm, and I'm like, it is getting completely covered by eosinophils. Now, if you do have a parasitic worm infection, because the eosinophil's job is to kill them, you're generally going to have an increase in how many eosinophils you have in your blood, which is called eosinophilia. So, just large number of eosinophils indicates that there's a helminth or a worm infection, or also an allergic reaction. Now, and I'm like, still other non-phagocytic killing can happen. It's not only the eosinophils that can do it. And I'm like, the lymphocytes can do it too. And I'm like, lymphocytes, there is a specific type of lymphocytes. There's multiple types of lymphocytes. But one specific type of lymphocyte is called a natural killer lymphocyte. That's its job, is to go around killing cells. Now, the two main cells that it tries to target and kill are virally infected cells, because lymphocytes indicate virus infections. So it's trying to kill virally infected cells, and it's also trying to kill tumor cells, the ones that are growing uncontrolled. And I'm like, luckily it can differentiate from normal body cells to not kill it. And I'm like, it recognizes proteins on the membrane from normal body cells versus infected body cells or some type of abnormally reproducing body cells. And then one more non-phagocytic killing cell are the neutrophils. They produce chemicals that kill any type of bacteria invaders nearby. Neutrophils are generally involved in bacteria infections, and a lot of times they can generate these extracellular traps, these little webs. It looks like a big old web, and I'm like, it binds to and kills the bacteria. So they trap bacteria, and then they produce chemicals to kill the bacteria. And I'm like, you can see these are some little red bacteria stuck in one of these traps that a neutrophil made. A third chemical defense is nonspecific. And I'm like, well, the third chemical defense is nonspecific, not chemical defense, but the third specific process is nonspecific chemical defenses. And so it's not specific because it's anything foreign. It's not specific for a specific virus or an absolute specific bacteria. But it's a chemical. They're called toll-like receptors. And I'm like, now, toll-like receptors are proteins found on surface membranes of phagocytic cells. And so again, these are cells that are eating, and I'm like, and they have surface membranes on them. And I'm like, this kind of a fancy little membrane or fancy little protein found on them. Now, what these phagocytic cells do with these is that they will bind to pathogen-associated molecular patterns. PAMPs, as they shorten it. Everything has to have an acronym. Now, what these phagocytic cells really are doing with these proteins, and I'm like, is they are binding anything that's associated with a pathogen, things that are not associated with us. So examples of things, bacteria and viruses, that they have in common that we don't have in common is one, peptidoglycan. And I'm like, that is a pathogen-associated pattern. I'm like, none of the cells in our body have NAMs and NAGs that make up peptidoglycan. So that's a pattern that these phagocytic cell proteins can recognize, bind to, and target for destruction. Flagellin is a protein found in the flagella of bacteria. Yes, human cells, the sperm, can have flagella, and I'm like, have a flagella, but it's not made of the protein flagellin. That is a bacteria-specific protein. And then double-stranded RNA. None of the cells in our body have double-stranded RNA. That's a specific pathogen-associated pattern, generally associated with viruses. Now, once these phagocytic cells with their little proteins on them recognize some of these unusual things that only pathogens have, and I'm like, they're going to trigger a couple different responses. One, they can trigger apoptosis, which truly just means cell suicide. It tries to encourage that pathogen to kill itself. It's like, are you sure you want to be here? Are you really sure? I don't think you want to be here. You might just need to kill yourself off now. And it's called apoptosis. It's kind of cool that it can do that. And I'm like, so it encourages those pathogens to kill themselves. They can also cause the secretion of inflammatory mediators. So things that are going to increase inflammation, called interferons. And I'm like, that's my next slide too. We'll talk more about interferons. And I'm like, and two, they can also stimulate our adaptive immune response or our adaptive immunity, which is chapter 16 we'll get into later. But I'm like, these specific proteins recognize these structures and then trigger other things to happen. Now, those interferons. Now, interferons are proteins. They're released by host cells, so human cells, and I'm like, to inhibit the spread of viral infection. So if you have a virus that has gotten into your cells causing an infection, our body is trying to figure out a way that those cells can communicate to try to prevent the virus from reproducing. And I'm like, and I'll show my little picture with it. Now, this particular protein, unfortunately, and I'm like, can cause a lot of the symptoms that that's usually associated with a viral infection. You're tired, muscle aches, chills, fever, all these things. It's not the virus that's causing this. It's your immune response trying to get rid of that virus that's actually causing it. And so knowing that you have all these symptoms is actually not a bad thing. That means your immune system is working. It is fighting to get rid of this invading pathogen. Now, how an interferon works. So you have two cells here, two host cells, two human cells. One gets infected with a virus. The virus got in. And of course, viruses will do what bacteria do. They try to reproduce. But the virus got into this host cell. Now, and I'm like, once this host cell, and I'm like, that has this virus, and like gets in, and I'm like, there is a gene on our DNA that can recognize that you are infected with a virus, and it will switch this interferon gene on. So we switch on the gene. The host cell's like, oh, I've got a virus in me. I'll flip on my gene, and it starts to produce these interferon molecules, these proteins, which on this picture are little red triangles, are little interferon proteins. Now, these interferon proteins are going to get released by this infected cell. And this protein will actually go to the neighboring cell, any neighboring host cell, any neighboring human cell. It will bind to that cell. There are receptors on our cells that recognize it. And I'm like, and then it will tell our DNA to turn on genes to prevent proteins, or to prevent viruses from reproducing. So now all of a sudden this cell's like, hey, I was just told, because this is what was just told, and I was just told that there are viruses around. We should really arm ourselves, and I'm like, be prepared. And so now this cell, the second cell, is prepared for viruses. It makes an antiviral messenger RNA, which just makes this protein that blocks that virus from reproducing. Now, the good and bad. One, this cell that got infected with a virus will still eventually die. It got infected with a virus. But luckily, before it died, it made sure to tell any of its neighboring cells, hey, there's a virus around, please arm yourself. And all the neighboring cells are now prepared for it, and the neighboring cells live. So it blocks interferon, or it blocks viruses from reproducing. It's awesome. It's a little way for our cells to communicate with each other. Now, your book shows the same thing. You have an infected cell, you have an uninfected cell. Throw it all up there. Virus goes into the infected cell. The infected cell's like, here's my interferon, IFF. IFN is their abbreviation for it. And I'm like, I'm going to, start making this protein to tell my neighboring cells, and I'm like, that there's viruses around. This protein goes over, tells this cell, hey, there's viruses around. And I'm like, it starts to make these proteins. And I'm like, that yes, block viruses from reproducing, the little green circles. And I'm like, they block viruses from reproducing. This cell lives. This cell, unfortunately, still dies. But it saved its neighbors before it died. Now, another chemical, and I'm like, that can help protect against invaders, it's called a complement. It's really just a whole group of proteins. There are a whole bunch of blood proteins. There are over 25 found in your blood serum. And I'm like, and really I only care about the end result. And I'm like, yes, there's over 25. We all call them C something for complement protein 3 or complement protein 5A. And I don't care about the numbers and letters. But, and I'm like, these specific proteins are activated by foreign cells. So some foreign cell got in, or any type of antibody binding with a specific antigen, usually to a foreign antigen that it recognizes. What these proteins will trigger is inflammation and fever. Again, not always a bad thing, which ultimately will cause the lysis or the destruction of foreign cells. And so I'm like, it eventually, this inflammation and fever caused by these complement proteins, and I'm like, causes inflammation, fever, causes the destruction of foreign cells. Now, as I've mentioned before, inflammation is not always a bad thing. It is a process from our body that tries to decrease, and I'm like, try to keep those pathogens under control. Now, inflammation just means it's a non-specific response to tissue damage from various causes. So there's some type of damage. In our case, we're going to go, there's some type of damage from an invading pathogen. Now, your basic symptoms of inflammation: redness, heat, swelling, and pain. Now, the good parts of inflammation is, one, your blood vessels dilate. That causes the redness. They're dilating, they're getting bigger, you have more blood flow to these areas. This is not a bad thing, because as your blood vessels dilate and get larger, it allows some of these phagocytic cells to walk through the walls easier. And I'm like, so as the blood vessels are dilating, getting larger, sometimes these things can now sneak through their walls and get where they need to go. And I'm like, now that complement protein activation, and I'm like, that it's recognizing there's something foreign, and I'm like, increases inflammation. This is showing that, yes, it's, recognizing, and I'm like, there is something foreign. It will cause inflammatory mediators to trigger inflammation. Now, there are two kind of groups of inflammation: short-lived, long-lasting, or acute and chronic. Acute means it is short-lived. You have inflammation for a short period of time, and this is beneficial inflammation. It means, and I'm like, that in that short period of time with that inflammation, blood vessels got, wherever they needed to go, your white blood cells, and they'll eventually get rid of whatever condition that caused it. So if it was a bacteria that caused inflammation, and I'm like, we have inflammation till all the bacteria are gone, and then the inflammation goes away. Problem becomes with chronic inflammation. Chronic means long-lasting. This can become harmful. This means you have inflammation of tissue that doesn't go away. And when you have inflammation of tissue for long enough, it can actually cause tissue damage and result in other diseases like arthritis. And I'm like, rheumatoid arthritis, that's when you have inflammation around those joints. And I'm like, that long enough inflammation actually causes permanent damage to those joints. And so I'm like, that is not a good type of inflammation. But that acute inflammation is good. Now, and I'm like, this is just showing those dilating, the effect of the dilating mediators, that something triggered inflammation. This is showing what your capillaries look like before, what your capillaries look like after. Again, it's a whole lot wider. And I'm like, it just means that you now have an increase in blood to those particular areas. And I'm like, and that also, by having that dilation there, means, yes, you're going to have that red appearance, and you're also going to have the heat associated with swelling. So if your skin all of a sudden is really red and really warm, a lot of that's just because you have lots of blood flow making it red, and with all that blood flow, it's bringing heat to the surface of your skin, making it feel hot. This is showing how when it inflames, that capillaries kind of separate out, and you can get some of those white blood cells sneaking through there. And I'm like, the diapedesis. Also, by having those capillaries kind of expand out and get a little bit larger, yes, you can have some fluid loss out of your blood. And I'm like, which can also cause that edema. And I'm like, in the swelling that's associated with inflammation as well. That's some of the fluid literally just leaking out of your blood vessels. And then our last process that can try to get rid of some type of invading pathogen is a fever. Again, a fever is not always a bad thing. What a fever is, it just means your body temperature is over 37 degrees. Now, what triggers a fever is a pyrogen. And if you think of pyro, I'm a pyromaniac, maybe some of you are too. Pyro means fire or heat. Gen means to generate or make, so a pyrogen makes heat. And so this is a substance that triggers the hypothalamus. The hypothalamus controls body temperature. It triggers the hypothalamus to increase our body's core temperature above that 37 degrees. Now, things that are considered pyrogen, things that are substances that will trigger the body to up its temperature, are bacterial toxins, like those endotoxins of gram-negative, found on the gram-negative outer cell wall, or cell membrane. The cytoplasmic contents of the bacteria that are released, and I'm like, by lysis. And I'm like, whether it's an endotoxin, whether it's exotoxin. Antibody antigen complexes. Anytime you have any one of our antibodies recognizing a foreign antigen and sticking, that will trigger fever, meaning our body is realizing there's something foreign there. And then there are also pyrogens that are released by the phagocytes once they have actually started to eat bacteria. And so phagocytes too, as they're eating bacteria, will actually start to release various pyrogens that increase your body temperature. Now, why a fever is not a bad thing, although you may feel like it's bad, is one, it enhances the effects of interferons, the things that are trying to stop viruses from reproducing. And I'm like, again, this is a good thing. If you have a viral infection, you would like your viruses to not be spreading into more cells. And I'm like, it's one of those, my whole little thing. If the fever is not too bad, if you have a fever and I'm like just slightly above body temperature, try not to take that ibuprofen if you don't have to. Obviously, if your body temperature, your fever is getting like 102, and I'm like, or it's affecting your daily life, and I'm like, yes, please take something. But if you can survive a slight fever, try to, because that fever is actually, will help you actually get better faster, especially if it's a viral infection because of the interferons. Also, by having that increase in temperature, it inhibits microbe growth. Microbes like to grow, our bacteria like to grow at about 37 degrees. Well, if your body temperature is 38 degrees now, it's not its optimal growth, and bacteria are not going to grow as quickly. And so again, not a bad thing to keep that fever. And also, that increased body temperature really does speed up various types of reactions in our body. It can enhance phagocytes, so these eating cells actually are a little more effective when your body temperature is up. Tissue repair, the process of tissue repair increases, and it also enhances the activity of our lymphocytes, those cells of the specific immunity, which might be necessary to fight off whatever got in. So again, if you can survive the fever, if it's not too bad, do it. And I'm like, you might be sick for a shorter period of time. So that's the end of all of our innate immune response. And I'm like, chapter 16 gets into more of our memory, and I'm like, our specific host response or immune response.